Good morning. All right, we're going to finish our talk about acids and bases today. Um, what else did I want? I have to apologize. I won't have the exams done today. There's still going to be some grading left to do there, so I will get those posted as soon as I can, and then I'll let you know when you can come pick them up if you want. It'll be next Wednesday probably. All right. So where we left off last time, we were talking about conjugate acids and bases. So let's review that real quick here. If we look at an equation like this, it doesn't matter what kinds of acids and bases we're looking at. One thing we didn't talk about last time was how do we even identify a reaction as a reaction between an acid and a base? And while that question gets more complicated the further you get in chemistry, for our purposes, we can go back to that first definition, that Bronsted-Lowry definition, and say that a acid-base reaction occurs when we are transferring a hydrogen ion, an H plus ion. So H plus is going from one molecule to another. So if we look at a reaction like this first one here, we can say, all right, what is changing as we go from products to reactants? Well, we start with HCN and hydroxide, that's hydrocyanic acid and hydroxide, and then we end up with water and cyanide ion. And so what's happening here is the hydrogen is moving from the HCN to the OH to make HOH or H2O. So since we can see that there's just one hydrogen moving, that tells us that this is indeed an acid-base reaction. So then we can identify, well, what's acting as an acid and what's acting as a base. So in the forward direction from left to right, the species that loses a hydrogen is the acid, and the species that gains it is the base. So this is the acid, and this is the base. And then each of those is going to have a conjugate pair on the other side that represents the result of either gaining or losing a hydrogen. So the HCN is going to get paired up with the CN minus, and the OH gets paired up with the water. And those are the conjugate pairs in this reaction. Notice that not only does one of them lose the atom of H, like CN, HCN becomes CN, but also the charge changes because it's not losing neutral hydrogen, it's losing hydrogen ion, +1. So if you have a neutral species like HCN with no charge, and then it loses a positive, it's going to end up being -1. And similarly, if we start with hydroxide at -1, and then we gain a +1, -1 plus +1 is 0, so that species then is neutral. So when you're drawing acid-base reactions, when you're transferring that hydrogen, make sure that you're also correcting for the charge, which is going to change as well. All right, you can try these two. Let me know. We did one similar to this, but try those two and let me know if you're having issues there. And we saw some of these before. So now let's talk about the concentrations of acids. So we talked about strong and weak is about how they break apart, whether they form ions or not. If they form ions, if they entirely form ions, that is a strong acid. If they only partially form ions, that's a weak acid. But then we can also measure how much hydrogen or hydronium is in solution. So if we look at this kind of first strange reaction that we drew last time, we can talk about the acid-base reaction between two identical molecules of water. Water and water actually do ionize. So when you have pure water, pure deionized water, that's just H2O, there actually is some hydroxide and some hydronium in there, and there's an equilibrium going back and forth. Now, there's not a lot of that in there. There's mostly just neutral water, but there is a little bit of this. And it's enough that we can actually measure that concentration. So when we measure that concentration, we find that each of those species, both hydroxide and hydronium, have a concentration of about 10 to the -7th molar. All right, now that's small. In pure water, a 10 to the -7th molar concentration, if we remember our scientific notation, is that, right? 0.000001 molar. So 0.000001 moles per liter of water are hydronium. And that's, it's a small number, but compared to like Avogadro's number or something of when you think about how many actual molecules are in there, that's actually a decent amount. It's a measurable amount. And so as it turns out, the hydroxide concentration is also that because it's even. And so when we talk about a neutral pH or a neutral solution, what we're talking about is a solution where the hydroxide and hydronium concentrations are both 10 to the minus 7th molar, like in pure water. And so you can do some of this math here, but the important thing is that this pH is a measure of the hydronium ion concentration, and it's shown here. It's the negative log of the concentration. I'm going to also introduce a notation here that you might not have seen before. When we put brackets around a molecule like this, we're talking about concentration. So if we take the negative log of the hydronium ion concentration, we get the pH. Now, why does that work? What's going on here with log? Well, if you remember back to, I don't know, middle school, elementary school math class, whenever you did logs, I know it's probably been a while for most of you, but a log is a mathematical operation that returns the exponent. So if you take the log of 10 raised to a certain power, you get the power back. So the log of, let's write this down here instead of just talking about it. The log of 10 to the minus 7 is minus 7. All right, so log returns the exponent of a power of 10. If it's like scientific notation, some number times 10 to the minus 7th, well, then you need a calculator to do that, and you'll get something in between this and the next exponent, whatever it might be. So we've changed the objectives a little bit in this class with regard to this calculation because different calculators have different capabilities. But if you see a nice even power of 10 like this, you should be able to figure out the log just by looking at the exponent. And so then we also put a negative in front so that negative 7 becomes a 7. So instead of dealing with these big, or I guess really, really small numbers like 10 to the minus 7, 10 to the minus 14, we're dealing with nice even numbers between 1 and 14, 0 and 14 actually. So you have pH, when you take the negative log of that hydronium concentration, you get a nice number that is somewhere between 0 and 14. So right at 7 is a perfectly neutral water solution where the hydronium and hydroxide concentrations are equal. They're both 10 to the minus 7, and so the pH is 7. As the hydronium ion concentration increases, so if you add acid to water, you increase the hydronium ion concentration. And so you're getting bigger and bigger numbers. So instead of 10 to the minus 7th, maybe you've got 10 to the minus 4 or 10 to the minus 3. Those are bigger numbers, right? 10 to the minus 4 would be this. 10 to the minus 3 would be that. Those are bigger numbers than 10 to the minus 7. But when you do the negative log, you end up with a smaller number. So that's why lower pH means something is more acidic, because a lower pH corresponds to a higher hydronium ion concentration. So there's more hydronium in a solution with a lower pH. There's less hydronium in a solution with a higher pH. And so this gives us what we call our pH scale, where you have strongly acidic stuff way down close to 0, then weakly acidic, then you've got neutral in the middle. Now we say perfectly neutral is 7, but in practice, neutral is really like between 6 and 8. So it's, again, there's no like official rule of this is absolutely neutral, but generally between 6 and 8, we would consider a solution to be neutral, and then it would get more basic and then strongly basic as it gets to those high numbers. So what do those high numbers mean? Well, if let's say a pH is 14, that means that the hydronium concentration is really small. It's 10 to the minus 14 molar. That's a really small number. So that means that there's a much higher hydroxide concentration in that solution. All right. So let's do one of these together. So if our hydronium concentration is 1 times 10 to the minus 10, then the pH is just that exponent. It's 10, and that's basic. That's over here on the scale. And so you can do the rest of those. That's as easy as it is. All right, but what happens if, let's say we're dissolving sodium hydroxide in water, and we know the hydroxide concentration, but we don't know the hydronium concentration? Well, it turns out we can figure that out as well, because the pH and the pOH added together, the pOH being the negative log of the hydroxide concentration, those have to equal 14. So if our hydroxide concentration is 10 to the minus 2, our pOH is 2, and then our pH is 12. And that would also be a base, right? Because we always kind of measure things based on the pH. We can use the pOH to help us in that way. Let's go down here. If the pOH then is 10 to the minus 12, or sorry, if the hydroxide concentration is 10 to the minus 12, the pOH is 12, and then the pH is 2, and that's acid. So the pOH and the pH have to add to 14. We can get the pH or the pOH from the corresponding hydronium or hydroxide concentrations. And we can go backwards as well. So we can say, let's take a look at number 12 here. Comparing a solution of pH equals 5 to a solution of pH equals 1, which has the higher concentration of hydronium ions and which is more acidic? Well, we can figure out those concentrations by doing the opposite of the negative log, which is raising something to its negative exponent. So a pH of 5 means that our hydronium ion concentration is 10 to the minus 5 molar, or the way we would normally write that is 1 times 10 to the minus 5 molar. A pH of 1 means that the hydronium ion concentration is 1 times 10 to the minus 1. And so which one is a greater number? What's the higher, that's molar, what's the higher concentration? Well, the second one, right? 10 to the minus 1 is 0.1 molar. 10 to the minus 5 is 0.00001 molar. So this is much, much bigger. And so that's going to be the higher concentration of hydronium ions. And we didn't necessarily have to do that. We could have just noticed from the pH, lower pH means more acidic, means higher concentration of hydronium. The next question is the opposite. Comparing a solution of pH equals 8 to a solution of pH equals 11, which has the higher concentration of hydroxide ions and which is more basic? Now, in this case, since we're asking about the hydroxide ions, we're going to look at the opposite. So if the pH equals 8, then the pOH equals 6, because they have to add to 14. And that means the hydroxide concentration is 1 times 10 to the minus 6. In the second example, or the second one in the question, the pH is 11, which means the pOH is 3, and the hydroxide concentration is 10 to the minus 3. So which one has the greater hydroxide concentration? The second one. Right, much bigger number there. And so that one's going to be more basic. So that's how you use pH to figure out concentration. You use concentration to figure out pH and then pOH. And then from that, we can rank how acidic or basic a given solution is. Notice this has nothing to do with strength. It's not strong acid or strong base. Those are different definitions that we went over last time. This is about higher and lower concentration, more or less acidic. Okay, so you can then answer these questions and see if you can figure them out. Let me know if you have questions. All right, let's predict a product of an acid-base reaction. So now, up to this point, we've seen just the things that are acting in the acid-base reaction. So for example, the one we looked at earlier here today, we had OH minus, right? Hydroxide ion reacting with the acid so that we could have this nice conjugate acid-base pair. But in reality, you can't just get a bottle of hydroxide ions. Hydroxide is always going to come with some sort of a counter ion. So like in this example, you've got HBr, the acid, hydrobromic acid, and then we've got the base as potassium hydroxide, not just hydroxide. So when we write the acid-base reaction, when we have the ions there, we have to think about what's really happening in solution, and that's called a double replacement reaction. So in solution, let's look at this next one together. In solution, HCl is going to be hydronium and chloride, and KOH is going to be potassium and hydroxide. Those ions are breaking up in solution because it's an ionic compound soluble in water. So we're still doing an acid-base reaction where the H is going to go with the OH and form water. That's always going to happen. But then what's left over is potassium ions and chloride ions. And rather than write those separately, we usually put them together, even though in an aqueous solution, they would in fact be separate. You'd have potassium ions, you'd have chloride ions. But just for like organization of the reaction, we usually do it that way, and that way we can balance the reactions and all of that. And this is particularly an issue where we have things like, let's look at this bottom one here. H2SO4 is what's known as a diprotic acid, meaning it has two hydrogens instead of just one. So when those get neutralized, again, we're going to form, the hydrogens are going to go with the hydroxides. We're going to form water. And then the other ions are going to be the rest of the reaction. And in this case, we need to remember some things about our ions. We need to know that barium is +2, and we need to know that sulfate is +2, or is -2, sorry, so that we can build that compound accordingly as barium sulfate. And then we can balance this reaction where we would actually get 2 waters when those combine. All right, let's do this one as well. It's kind of a part of a question up here that you can read, but I just want to look at the reaction. HCl plus MgOH2 is magnesium hydroxide. So in this reaction, again, we've got an acid HCl, we've got the base hydroxide, so we're going to form water. But then we have to figure out what our other salt is. So that's going to be the other stuff that isn't H or OH, and in this case, that's Mg and Cl. But we can't just write MgCl because that may not be the compound that's made from magnesium and chloride. So it's still important to build those compounds the way we did several chapters ago, to recognize that magnesium is a +2 ion and chloride is a -1 ion. And so our product is going to be magnesium chloride, MgCl2. All right, those compounds still need to be written correctly. So if you need to go back and review some of that stuff from naming and building ionic compounds, this would be the time to do that, because we'll definitely be using that again. So make sure you try these reactions out. Let me know if you have questions. You should be able to look up answers. These are common reactions and equations, but if you can't find something, just let me know and I'll tell you. All right, last things we're going to talk about is buffer systems and blood. All right. So what happens if you take pure water and you add just a very, very small amount of strong acid, like just a drop of HCl or something, all of a sudden that pH will drop because now it went from being 10 to the -7th concentration of hydronium ions. Even if you just add a little bit of HCl, you're still probably changing that by a few orders of magnitude. So if you put 1 drop of HCl in some water, you're probably going to drop that pH from 7 all the way down to like 1 or 0. It's going to go really fast. Acids and bases, same thing with strong bases. If you put a drop of really concentrated sodium hydroxide, again, you're going to raise that pH substantially. And often we don't want that to happen. We want a solution that can absorb some acid or base being added to it. And those types of solutions are called buffers. A buffer is made from a weak acid and its conjugate base, a mixture of the two. So here's a Lewis structure of acetic acid, which is a weak acid. And then here's its conjugate base where the hydrogen is missing. And this is called acetate. And so there's a buffer solution could be made from those two things. So it would be, again, you can't add an ion by itself, but something like sodium acetate. And then you would have a buffer solution. And the way that would work is what happens is if you added some strong base, hydroxide ion, the hydroxide ion would get rid of this hydrogen. It's called deprotonate. It would do an acid-base reaction where it would pull off this hydrogen to make water. But because it's a weak acid, the solution is still mostly neutral because this equilibrium is going to make sure that there's still plenty of neutral acetic acid in solution. And the same thing with a strong acid. If HCl is added to solution, well, that H is going to bind up with the acetate ion and form neutral acetic acid. So the positively charged hydronium ions aren't really going to be in solution. They're going to be captured by that acetate and become neutral again. So the pH doesn't change. Now there are limits, of course. Once you run out of weak acid and conjugate base of weak acid, once you've used it all up by adding a whole bunch of acid or base, then it will start to change its pH quite a bit. But up to that point, you can actually control the pH and stop it from moving. And you can control it at any pH you want. If you go on and take more chemistry, you will learn how to calculate this. But depending on the balance of acid and conjugate base, you can make a buffer of any pH you want. And then when you add more acid or base to that solution, it won't change its pH. It'll maintain pH. And that's really important for a lot of systems that are pH dependent, especially for example, biological systems. And I don't see that here, so I'm just going to put it here. Put it here. Your blood has an extremely narrow pH range, 7.35. So not exactly perfectly neutral at 7. It's just on the very basic side. Still, we would call that neutral. But it can really only vary a little bit from there. Probably like 0.7 from 7.35 to maybe 7.4, something like that, around that range. If your blood pH varies more than that, you get serious problems. The terms for those are acidosis and alkalosis. Acidosis is when your blood pH goes too low, and alkalosis is when your blood pH goes too high. And if either of those things happen, they cause major problems in your body. And the way that your body regulates pH is with carbon dioxide. So when when your cells undergo respiration, they produce carbon dioxide. Carbon dioxide and water make carbonic acid. And this is goes back and forth. And then carbonic acid can also dissociate into hydrogen or hydronium and bicarbonate. And so this kind of becomes the buffer system where you make carbonic acid, which can then become its conjugate base, bicarbonate. And these things, it's almost like a circle. These things can all become each other. They react, they go back and forth. But the amount of carbon dioxide in your blood can control your pH. And that's why, for example, when you hyperventilate, when you're breathing too hard, you can actually go into a little bit of a state of alkalosis, because the carbon dioxide that's giving you the acid, you're exhaling too much carbon dioxide. And so your blood pH can drop. You can end up, your blood pH can raise. The acid in your blood, the acid concentration drops. The pH goes up, and you can get into trouble that way. There's other ways also that you can go into acidosis or alkalosis because of what your liver's doing or your kidneys or whatever. But generally, that's controlled by carbonic acid and the formation of that in the blood. So the other thing that happened, or that's happened lately, is there's been a lot of dietary stuff about pH. You've probably heard this, that like there's products like alkaline water, or that you need to not eat too much acid. All that stuff is essentially nonsense. You can't change your blood pH by what you eat. You can affect other things, like if you have stomach problems, if you have reflux disease, sometimes acidic substances can aggravate that. But in terms of affecting the pH of your blood and the way your body works, nothing you consume really has an effect on that. So a lot of that stuff is just nonsense meant to sell you more things. You don't need to pH adjust your water before you drink it. You don't need to make sure that you're eating particular foods that change the pH of your blood. That doesn't really happen. If the pH of your blood changes, you are in big trouble. And luckily, we all have systems in place in our bodies to make sure that doesn't happen. So blood is buffered at about 7.35 by carbonic acid, which makes sure that the pH doesn't change significantly. All right, so you can try to complete some of these things. Again, make sure you take a look on Blackboard at the objectives. These are meant for you to look them up and sort of figure them out, not stuff you need to be able to know and do on a quiz or a test. I'm also, I think I figured out what's going on. I have to talk to tech support one more time today, but I think I figured out what's going on in Blackboard, so I should be able to have the assignments and the quiz up there shortly for you to complete. All right, let me know if you have any questions or if anything else comes up on this. We're really getting toward the end. I'll see Group B at lab today for the fat extraction, and then we'll do, I believe, one more lab, maybe two, the solutions and colloids, and then I don't know. I'll have to look at it. Anyway, I'll see half of you today and the rest of you soon. So bye, everybody.